Hello, hello, good morning, good evening, good afternoon, wherever you are. Welcome to the second workshop for today. We will be covering anonymous credentials from ECDSA. We have Abhishek from Google who will be covering the topic, and I will be inviting him on stage in a second. For those of you that missed the previous workshop from Justin Drake, no worries, everything is recorded and we'll make recording available in the next 24 hours and it will be added to the Hacker Pack along with all the options. Hello, Abhi. Welcome on the stage.
Hello.
Hello, hello. Everybody, please make sure to say hi in chat and make sure to ask your questions within the questions tab. That's the question button next to the chat section, and please make sure to post there so that Abhi can go through these as he goes along with the presentation.
Hello, everybody. Should I go ahead and try to present?
Share your screen, yeah. Take it away. I will be in the audience as well and come back on stage if anything is needed.
Okay, great. So thank you, everybody, for inviting me to give this talk, especially Tian Cheng and Jen Fei. Appreciate you inviting me to talk about this work. Again, feel free to try to interrupt me. I don't think you can, but I'll pop back to the question window if you have a question and try to answer it right when you have it. But otherwise, in my view, I can only sort of see my slides at one time. So let me go ahead and tell you about this work. So first of all, this is joint work with my colleague Matteo Frigo at Google. And all of this work is on this paper on ePrint that we've released last year. And we're sort of concurrently trying to work to try to get this protocol into some sort of implementation that's deployed and so forth. But let me try to first, so my presentation, I'm going to try to explain kind of the high-level problem that we solve, and then our specific solution, which of course relies on SumCheck. So this type of academic research that I did and Tian Cheng did in his PhD, and a handful of other people like Justin Thaler and Yupen Cheng, some of the other people that are speaking at this event, we've all kind of embraced this SumCheck approach to building zero-knowledge systems. And our approach in this work is slightly different than other work in the literature, but it's I think they're all essentially this is the best technique among all of the ZK systems, and essentially the choices that I've made here are just one selection, and there are possible other ones. So let me get to the main problem. So managing and using digital identities with anonymous credentials. So essentially, what does that exactly does that mean, and how does that essentially work? So I'm interested in using zero knowledge for this digital identity problem. And so the idea is that some credential issuer, like let's say the DMV or a passport agency and whatnot, they in the future or even today, they are going to issue digital credentials to their users. So today they issue physical credentials like cards and books and so forth, passport books. But eventually, and even today, some states, there are about 5 of them in the United States, they offer you a digital credential, i.e. some sort of signed document that asserts identity attributes. And we'll get into specifics of how they encode those and so forth later. And there are many candidate systems that have been used today. So for example, the ISO has this MDoc standard, which they've written this thing about. There's this other thing called SDJOT, which is like selective disclosure Java Web Token or something like JavaScript Web Token. And both of these are standards for doing exactly this task of some identity issuer basically giving you a digital credential. Today, again, I say it's a state-issued thing like a DMV or a passport agency. But eventually, like, for example, the EU, they imagine that essentially every organization begins asserting properties of their users, and then users essentially have some way of managing these things and then making more complex statements about themselves to other parties. So what do you do with the digital credential? One of the first main use cases, and this is from this europa.eu website, is that age assurance, this task of essentially proving that you're a user that's age is over 18, you'd like to basically maybe even anonymously or pseudo-anonymously kind of assert that you're over 18 without really revealing anything else about yourself. And we're only going to discuss credentials today that at least at minimum support this selective disclosure property. So for example, a digital credential may include many things like age, eye color, address, driver permissions, blood type, organ donor status, et cetera, et cetera. But maybe you just want to disclose that your age is over 18 without actually even revealing your age. How does that happen in the status quo? How do I propose it should happen in the future? So let me go back and see if anybody has a question about that. Nobody yet. Okay, good. All right, so let me give you a quick example of the MDoc format that's used today. And how does it actually work? So this is kind of exactly an encoding of that format, and I've elided a few extra details, but I've highlighted the important ones. So of course, this document has a bunch of stuff about what version number and what algorithms are used, etc. But ultimately, it has this section called value digests here in the middle. I hope everybody can see my little cursor here that I'm using, but it's also highlighted in green there. And this value digest is going to include a number of salted hashes of attributes. And so I've highlighted 0, but let's say this credential has 34 attributes that let's say are included in this credential. Later on, I'm going to tell you about this yellow part, but right now we can sort of forget that. We can sort of see that this right here is kind of this double parentheses data structure is essentially the document that is signed by the issuer here. So they format a document in this format right here with salted hashes, they sign it, and they essentially give the user that signature. And what exactly is this salted hash? So for example, the 71CD thing, which was this green thing that I highlighted right here, that is essentially the hash. And the pre-image of that hash is essentially this particular string. And let me kind of break that string down. It includes this encoding, some encoding information, but the gray part right here is essentially a random salt, okay? And this green part right here is an encoding of the age over 18 property. That's exactly, it's the ASCII encoding that's underlined here in blue and this written in green, age over 18. And then this value F5 right here is the, CBOR encoding of true. So essentially, you can look at this string as essentially a special way of encoding that this user has age over 18 set to be true, okay? And it includes a random nonce right here, and its hash is here. So essentially, if I want to prove that I'm over 18, what I need to do is essentially give this entire red string, which is the pre-image of this 71CD string, okay? And so I give you the pre-image, and you yourself parse it and see that age over 18 is set to be true in this thing. And then you check that this 71CD string actually exists in the signed MDoc statement. So essentially, what you've learned is, in fact, there are 34 attributes that Abhi has. The first one is that, the hash of the attribute is 71CD, and the preimage of 71CD is this statement, which essentially includes, that states that I'm over 18, okay? And so essentially in an MDoc presentation today, the way identity is handled today by the ISO standard, and this is a standard that's implemented by 5 states and a few European countries and so forth. Essentially, the user, so there's a relying party, essentially the verifier in this thing, and they ask, for example, they request that they would like proof that you're over 18. They include this transcript that's used to basically end-to-end encrypt this flow. So this flow is meant to be over the web, but it's also meant to work between 2 phones, and so forth. Thus it needs to basically do its own end-to-end encryption. So in the first message, you essentially get the request and this Diffie-Hellman type of key exchange, first message. And in the second message, the user basically reveals this MDoc right here, this entire data structure, and then also gives the pre-image for the attribute that was requested. So I'd essentially give you this pre-image, the red string. And then I'd also give you this signature of the device public key of the transcript. And I'll explain exactly why that is needed. But essentially, if you look at the message transcript, it's essentially the full MDoc, the pre-image, and a signature. So it's rather compact so far. And then the relying party, in order to check this flow, they verify the signature of this full MDoc by the state of Massachusetts, let's say, or the issuer. They parse the MDoc to find the device public key. They verify the signature of this device publicly. I'll explain why that's needed in a second. And then, as I said before, in steps 4 and 5, essentially are to check the pre-image, states the pre-image of this essentially indicates that I'm over 18. And for example, the credential expiry condition, like this credential expires. If you look at this last part of information, it expires in a certain time period, and the verifier also needs to make sure that the credential hasn't expired. Okay, and so that right there is an example. So that is currently how identity on the internet is handled. Now this scheme, it doesn't have a zero knowledge at this point. It's just called selective disclosure. It has a number of flaws. So we're going to go through the flaws, but first I see that there's one question. In this kind of string, are there some letters in the end to check if the string is not mistyped, partially typed, like in the credit cards? So there is no redundancy in this type of credential format. There's nothing redundant about this to check for error correcting. There's nothing like that. Essentially, it is the error correcting is basically done at different levels. So for example, if it's done on the web, it's done over TLS, and thus that system already has a authenticity and integrity check. And if it's done over Bluetooth, for example, between two phones, then the Bluetooth layer already has essentially redundancy to guard against those type of errors. I hope that answered your question. So what I want to do now is I hope you kind of understand what the state of the art is today. These are protocols that are deployed, but they have some basic security problems, and now we're going to talk about those. So in fact, the first three big problems with these systems, the first one is copying, which leads to fraud, okay? And then the second one is tracking, and the third one is deployment. Let's go through the first one right here. So the first major problem that you should wonder about when you have digital credentials, what prevents some user from just taking their credential? You can just take I can just extract the credential from my phone and then give it to some other user and say, now you can just impersonate me, or you can prove that you're over 18 to any website that you want, okay? And in fact, if it's easy to root like an Android device, which it is, it's easy to copy the storage, then essentially someone can extract whatever this credential is and then essentially post it on the web, and anybody could essentially copy it and put it on their phone. And then essentially the whole system of digital credentials, the whole idea that you can prove something like this over the internet, that would essentially become unsound, right? If anybody could essentially, if you could make it easy where all I had to do is download a special app that had some other credential in there, that would essentially degrade the system of the whole system, right? And this is especially true if you have zero knowledge. If you have full zero knowledge about credentials, then this copying problem becomes really, really difficult, because it's very hard to, for example, revoke credentials if you're giving everybody zero knowledge proofs about credentials. If you just think about essentially that problem. And so, of course, the designers of this protocol have in mind a way to protect against this very basic attack, okay? And it all starts from the onboarding process. So I wanted to give a short little video about how these protocols actually work in practice, how you onboard today, how do you bootstrap a system where you take essentially physical credentials and make them into digital ones. And here is one particular instantiation. So you might have essentially instructions on how to onboard a digital ID to a wallet. This is kind of all test data, all basic sort of, you kind of take a scan of the front and back of your driver's license today, okay? And that's just to kind of currently identify you. And then the second major thing you need, all of the major schemes have this, which is a liveness check. And today that liveness check is done by essentially you taking a video. Now, it dynamically asks you to move your head in a particular direction. So it tells you to move it up or to the right or to the left, or 3 directions, and it kind of picks one of the 6 permutations. That's essentially to try to guard against very basic attacks where you try to play a video. And of course, there is some back-end scheme that very carefully checks whether essentially that video corresponds to the same person. That's either done by human or done by some AI system in order to make sure that the 2 people are correct. But this is just the first step of the onboarding. There's actually a hidden step that involves the secure element on your device, okay? And so that's what I'm going to talk about next here. Okay. So if you think about a modern phone right here, that essentially there's 3 levels of it. There's the application level where a wallet might live. There's an Android operating system layer where like there's this API called Strongbox, for example. And then there's the hardware layer of the phone where you might actually have a hardware secure element that, for example, can store ECDSA. It can generate ECDSA keys that only exist on that secure element. So some versions of like passkeys or FIDO2 authentication essentially use this type of secure element essentially to help you log in without passwords and so forth. So the idea is an issuer who wants to make sure that people don't copy credentials will do the following. When they onboard you, when they issue your digital credential, they will, of course, do that ceremony, that video ceremony that I showed you, but they will also ask your phone to produce a secret key that is signed by your secure element, okay? And so they will ask for the public key corresponding to the secret key. The secret key only lives on the secure element. That's the whole point of the secure element, is to prevent secret keys from being extracted. And so essentially the wallet part will ask for the public key from the secure element, and the wallet part will then send that public key to the issuer. Okay, and this is called a device-bound key, and that's what this yellow part is in this credential. So when the issuer verifies that in fact that's Abi corresponds to the same person in the ID that was scanned, okay, they're also going to get this device public key that is verified to have basically been created on the secure element. There's some mechanisms to make sure it's a key that was produced on the secure element, not just a random key. And the issuer will put this device key into the MDoc credential, and they will sign this entire message that includes the device public key. Okay? And now essentially, if you remember that protocol that I showed you here, okay, in addition to give you, when the user wants to basically give a proof about a claim, they give the full MDoc, they give the pre-image, and they also sign like essentially a nonce, which in this case they use that transcript message. They sign a nonce essentially using the device public key. And this relying party then verifies the signature under the device public key of this fresh message. And by checking that signature, essentially they have some assurance that this entire flow basically originated from a device that essentially has the secret key corresponding to the public key that is included in the credential. Okay, so let me go back and ask, that's kind of a complicated flow, but does everybody kind of understand how the device public key essentially is bound to the device because it was produced by a secure element, and thus anybody who succeeds in that particular flow actually had access to the same secure element that was used during onboarding. And essentially what this means is this device-bound credential makes it much, much harder to copy a credential. Of course, issuers can make sure that they only issue, like, let's say, a certain number of credentials to different devices, so maybe 2 per month. Like maybe I could lose a device and then I can re-onboard myself onto a new device, but maybe they'll basically prevent me from onboarding 5,000 new devices, right? So that's a limit. And now all of a sudden, even if I extract the credential from my phone, okay, the secure element was specifically designed to avoid extraction, right? It's like it uses hardware-based security to prevent you from extracting the device public key, the device secret key. And as a result, even if I can extract the credential, which is that signed document, I can give it to somebody, but they can't use it because they won't have a way to produce a signature under the device public key. Users can, of course, still share devices. I can give my phone to my child. My child could then prove that they're over 18 and do so and so forth. But this becomes a big inconvenience. It certainly limits the abuse at scale, okay? And this idea of like device-bound credentials is kind of it's considered defense in depth, and it's considered a required feature of any sort of like credential scheme that is intended to be deployed at scale. So anybody have any questions about that? Okay. Can issued credentials be time limited for their existence? Yes, exactly. Issued credentials can be time limited. So if, for example, I showed you right here a sample MDoc credential. The validity info essentially gives you the time period for which this validity info is signed, right? This is the document that is signed by the issuer, and the validity info essentially tells you the period, the valid from and valid until, during which the credential is valid. And as I mentioned before in this slide, let's see here, right? The step 5 right there is to make sure that the credential essentially expiry conditions are true. So now the relying party checks that the now time essentially falls between the valid from and the valid until. So that's how the first problem is dealt with. How do you prevent copying? Well, you require credentials to be held on to devices that have secure elements, and you involve the secure element every time you issue and every time you show a credential, okay? But now the problem is the following, okay? This device public key exists in every credential, and it's required information used to verify the credential show, okay? But this problem unfortunately creates a linkability problem, and this is a serious privacy problem, okay? And so let me try to explain this problem. So you have these 2 yellow strings now that are in every credential, and these credentials essentially, let's say Bob here uses basically asserts they're over 18 to service provider 1, okay, the top one, and then later that day they do exactly the same type of show for service provider 2. Now, of course, service provider 1 and service provider 2, they use different nonces and different parameters of the flow. However, in both cases, both parties receive that information. Like suppose service provider 1 asks for age over 18 and service provider 2 just asks for first name, okay? Both parties would receive this device public key, which, for example, I've just abbreviated here. Both parties would see session 1 with service provider 1 included this 9631 device key. And then session 47 with service provider 2 also included this 9631, right? So you can essentially see that these service providers may then attempt to link the sessions. So they may go to a data marketplace and say, hey, let's try to figure out all the information we can about our, quote, anonymous users. Let's try to link all the sessions and try to figure out what behavior they're doing, right? And this is a problem that we already see today on the internet with third-party cookies and tracking cookies, etc. Okay, the whole idea of digital identities and digital credentials was try to avoid tracking while asserting aspects of your identity. And so essentially the problem that was the solution that is used in order to prevent credential copying introduces a new problem, tracking, okay? And one solution could be, why don't you force users to get a new credential for every different service provider they use? Okay, so in the top one, I only use the device key that has 9631, et cetera, et cetera. I actually register a separate key that, for example, here, the separate device key is 787 that I use for the second provider. And let's say I deal with 1,000 websites every month. Then my device, my phone, let's say, keeps just 1,000 different credentials, one for each party, okay? So that, in fact, is a first-order solution, but it doesn't solve the whole problem because, in fact, the issuer of the credential, the DMV, they can always essentially collude with a relying party to identify users. So, for example, no matter what credential a service provider is given, like this one is given 787, right? The DMV, the one that issued the credential, they had, of course, check you, and they had to check your device key to make sure your device, they had to do some checks to make sure that it was issued by a secure element. And so they have the list of all of the keys that are basically registered by Bob. And so the DMV and the service provider can collude, and this is a very serious problem. The government that issues these credentials can essentially subpoena any website and then figure out every user that used that website. And that could be problematic in certain scenarios, and that's a very serious issue. The European Union has essentially flagged it as one of the problems they don't want, which prevents them from wanting to deploy these type of systems at scale. Okay, so that's The second problem, I'm going back to the questions here. I see a bunch of questions here. Let's see. Pragmatically today, when using passkeys, then using passkeys is the only way to move forward. Well, so passkeys are in fact a method for doing password authentication, but they don't assert any identity attributes, right? So indeed, a future work is essentially going to link passkeys with credentials. But passkeys right now would essentially allow me to create an anonymous account with any third-party website and allow me to re-log in to that particular website. But they don't allow me to assert any identity attributes to that website. So they're kind of orthogonal issues. Passkeys is for authentication, and these credentials are basically for asserting properties after you've authenticated about your identity, and trying to do that in a selectively disclosed way so that you don't have to give, like today, for example, if you want to prove you're over 18, many websites require you to take a picture of your ID and upload it, right? And that's really problematic. If that website gets compromised, then a picture of your driver's license can essentially be on the dark web, and that's, you know, that's really problematic for all sorts of other security protocols. The next question is, this feature requires device manufacturers to build in this kind of devices. That is true. So I don't have my phone here next to me, but essentially, most of the modern phones, like every phone that Google has produced in the last 6 years, all the Samsung phones, all the Apple phones, all of the all of the popular hardware providers, they include secure elements on their phones already because they use them for other purposes. For example, they use them for trusted boot, they use them for eSIMs, they use them for other type of security checks that they already do. For example, to check for rooting, check for jailbreaks, that kind of thing. So most modern devices already have secure elements, and Android already has this API called Strongbox, which either uses the secure element or runs in a secure enclave on the CPU of the Snapdragon or Tensor or whatever ARM chip. It runs on a secure enclave and thus simulates essentially a secure element and gives you that API. So any device that, for example, supports passkeys today already has this type of hardware that's needed. And then the last question is, if service providers can collude for de-anonymizing users, this isn't strictly zero knowledge. Yes, in fact, so that's the whole point. I haven't spoken about zero knowledge yet. And what I'm talked about so far is just what the status quo is and what the status quo, the problems that the status quo has. In fact, I've only gotten to 2 of them. The first one being tracking, which is solved by this device public key. First one is copying, which is solved by device public key. And the second one is tracking, which was introduced by this device public key. And the third one is going to be deployment. In fact, it's going to limit some of the solutions that one can use, and it's going to essentially motivate why we've taken the approach we've taken on this. So thank you for all of those questions. They're excellent questions. So the last problem I wanted to get to was deploying, okay? And in fact, issuers have a bunch of legacy infrastructure. So ideally, we would like to come up with a system where we don't have to change the identity credential system that's used today. In fact, this is the #1 motivation for this particular talk and for this line of work for me, actually. DMVs and national passport agencies and European governments and so forth, they all have a bunch of legacy infrastructure for issuing credentials, and in particular, creating signatures. They use things like this picture on the right, which is a hardware security module. These things are super expensive. They're like tens of thousands of dollars, and they only support legacy schemes like ECDSA and RSA, and they're hardened, and they're audited, and it takes a long time to basically come out with the next generation of hardware security model. And DMVs and so forth will take a long cycle to basically replace them. And so what is the main implication here? We believe that issuers are going to essentially stick with things like ECDSA and RSA, okay? And the main point is, if we want to do ZK for identity type of stuff, we have to embrace the kind of signature schemes that people currently use today, which are ECDSA and RSA. And the second thing is user devices in the field. So like Pixel phones and so forth, and Android and Apple, all the things I told you about, they have already deployed several billion units and those units have secure elements today, right? And those secure elements only support legacy crypto like ECDSA and RSA, okay? And so what this means is if you have a new zero-knowledge system that requires, for example, pairing-friendly curves, or that requires lattice signatures, or requires some special kind of scheme, essentially, then you may have difficulty deploying that. Now, that's not universally true, but that is true for certain schemes like BBS Plus and certain ways of deploying ZK. If it has to live in the secure element, if some part of it has to live in the secure element, that could basically essentially be foiled by legacy, by this idea right here that issuers are only going to support certain schemes and that user devices only support certain schemes. Okay, what I'm trying to say is that on phones, changing these two layers, the strongbox layer and the secure element layer, they take a long time, at least several years, because everybody, essentially, you have to convince manufacturers and Android to change these things. And then once those have changed, it takes several years before most users upgrade and get essentially the new devices. It's very hard to change secure elements in the field. So for example, you could imagine that's a big security risk if someone can externally update your secure element. It is possible, but it is very, very hard because there have to be a lot of checks to make sure that a third party like a nation state can't do it, because otherwise they can kind of subvert many authentication or login or security properties of your phone. So that's why essentially changing these things takes a long time. Means things like BBS Plus and other anonymous credential schemes we feel are going to be very difficult to deploy. What we think is a better idea is to use a ZK system that can essentially make statements about legacy crypto like ECDSA and like MDoc. And in fact, that's what ZK, of course, everybody knows that you can essentially make claims without revealing any extra information, okay? And what this means is we can take today's MDoc presentation, which includes this information right here, and which requires checks 1, 2, 3, 4, and 5, okay? And instead of sending this second message right here, okay, what we can do instead is send a ZK proof that all of the checks that would have been done, all of the information and all of the checks that would have been done actually pass. Okay, so all you need to do is give the proof, give the current time, and give the transcript, and then essentially the proof basically argues that all of these 5 checks would have passed. And that, in fact, is the goal that we're trying to essentially accomplish. And we have an implementation, a working implementation. It kind of essentially works, and essentially, if you take all of the current schemes right here, essentially you can boil them down into proving this kind of theorem, that the ZK theorem is essentially given the public values, which are the public key of the issuer, the attribute you want to verify, the transcript that's used for this device public key check, and the current time, you can prove that there exists an MDL, a hash, another hash, an index, et cetera, a bunch of witnesses that essentially satisfy all 4 of the claims that are essentially required in the current MDoc check. So this right here is what I consider the challenge problem. Let me go back to the questions here. So pragmatically today, when using, I think that one's answered, is the same as hard wallet uses. So I think, Katya, I think your question was, is this the same scheme that hardware wallets for cryptocurrencies use? Maybe, is that the interpretation? So it is true that hardware wallets basically use secure elements. In fact, so that is true. The secure element that I was talking about previously, like the ledger and those type of things I believe they have secure elements that store the secret keys that are used to sign. And the hardware wallet is essentially supposedly a single purpose device that only signs transactions for cryptocurrencies and is safe because it's not a full purpose OS, etc. And it's roughly the same scheme. Like normally these protocols use like a different elliptic curve. They use like the NIST P256 curve, and like most cryptocurrencies use a different ECDSA curve, etc. The next question is, could you elaborate on the transcript field? Absolutely. So the main idea behind the transcript, if you remember in this particular image, right? So when the relying party is asking for a bunch of attributes from the user, in order to make sure that the credential isn't copied, it's going to create a totally fresh challenge. It's called transcript because it's also used for a secondary purpose. I told you about essentially creating an ephemeral Diffie-Hellman key pair. But for this purpose, it's serving dual uses. But for the purpose that in this talk, transcript, you should think of it as just a random challenge from the relying party. And presumably this random challenge, the transcript, has never been used by the relying party before because it's like a random 128-bit string. And so it's totally fresh. And now what I do is I make sure that the device, the phone, the user, can sign that particular nonce, okay? And so it essentially prevents a replay. If I were to ask you to say, please prove that your age is over 18 and please sign the message foo, and I always ask you to please sign the message foo, then a cheater could basically go to someone who has, in fact, proven that they're over 18, essentially get that information, which would be the MDoc, the pre-image of age over 18, and the signature of the message foo, and they could just essentially keep replaying that same second message and using it to convince fresh relying parties that, in fact, they're over 18, right? So to prevent that, you basically make a totally fresh random nonce, and then you force the user to sign that totally fresh random nonce or transcript. I hope that kind of answers. Yes, exactly. Sorry, I just saw your thing. The transcript is like a response challenge part of the protocol, roughly speaking, to verify knowledge of the device public key. We haven't gotten to ZK yet. Essentially, the ZK part is the ZK part of this is giving a zero knowledge proof. This is the zero knowledge proof that given these four values, I know these private witness values such that all of these conditions hold. Namely, that I have a signature on the driver's license that was issued by the public key of the identity issuer. Okay, that mobile driver's license has a pre-image. Okay, I know the pre-image of that that essentially has the age over 18 equal true. Right. In other words, this red string that I showed way over here. Okay. This thing right here. So I know this red string, which shows that age over 18 is true. And the hash of that red string, which is this condition, I think hopefully you can sort of see this yellow part that's highlighted essentially checks that the red string is what's included in the arguments to the SHA-256 function, okay? And essentially its hash H2 is included in the mobile driver, is one of the salted hashes in the mobile driver's license, okay? And then the second part of it is that the device public key is also in the mobile driver's license, and I also know a signature under the device public key for the transcript that verifies. And finally, the very last green part of it is making sure that the mobile driver's license is still valid right now, right? And that's why the proof statement needs to include the current time, because the proof refers to the current time. Okay, so this is the game. Okay, so transcript, yeah, I think I see all the questions have been answered. Wow, I'm way behind time because I was going to show a little video demo here of this. We have this kind of proof working, but I just want to, the main point is it runs in about 1 second for a document about this big, which makes it essentially on the edge of like, it's considered to be fast enough for use on the internet. Let's see, I wanted to essentially in the last few minutes basically give a few ideas about our ZK protocol, right? So what type of zero knowledge protocols can be used for this problem. I hope I've essentially motivated the problem, what we're trying to do. And there are several approaches, like BBS Plus is a special purpose credential for signatures that runs extremely efficiently. It's elegant. However, it requires pairing-friendly curves. Similarly, like Gross 16, that is a family of ZK systems that have very, very short proofs, okay? Very, very fast verifiers, but it has a few problems. One of them is a very slow prover. And in fact, there is recent work on ePrint that essentially gives ideas on how to speed up the prover, essentially by reusing, like first making a proof and then re-randomizing a proof, okay? And that I think is very promising, but it has a, it also has a problem because if, for example, I encounter a theorem on the internet, please prove that your age is over 22 and your first name begins, or your first name, or let's say, or your zip code is 02445, right? If it's the first time that I've encountered that, then my phone will take 20 seconds to make that proof and then cache it for later. But the first time I make it, you're still waiting there 20 seconds to log in. So that's a big problem. Another big problem is that although you can pre-compute the proof about age over 18, we don't know how you can pre-compute the device transcript, that sort of the signature on the transcript by the device public key. We don't know how you can pre-compute that. That's a fresh signature every time. And of course, the biggest problem is that all of these proof systems need very large trusted parameter setups. And it's not, I don't see how it's feasible to, essentially require people to keep 1 gigabyte of their mobile device basically there for a trusted parameter. And there's probably going to be more than one, right? There's going to be the trusted parameter that is used in the US, maybe one that's used in Germany, the one that's used in the EU, one that's used in Asia. So it's unrealistic that you would essentially store several of these strings. So that leaves a few other schemes, and that's the kind of right side here. And Stark, Lajero, Hyrax, and all of the other works that Polyhedra does on its SumCheck prover, those only require hash functions. And essentially, that's where we think essentially these are the best right here. And this work today kind of focuses on this right-hand thing of SumCheck and a commitment scheme. And I just wanted to give you a few details about this. So I realize I'm running out of time here. So I wanted to essentially skip over essentially our technique. This is to use SumCheck and Lajero. And the reason we use Lajero again is that we want to use a commitment scheme that only relies on hash functions. And our previous Hyrax work used an elliptic curve kind of Peterson type of commitment and inner product arguments, but Lajero basically doesn't. And SumCheck, as you've seen in previous versions of this, is a very powerful protocol that allows you to prove essentially the sum over the hypercube of a polynomial is 0. And that can be used for essentially many verification protocols. Lajero is a proof system that essentially allows you to handle linear and quadratic constraints. Its downside is that it requires, the prover has to do a number theoretic transform on the size of the circuit and the witness, okay? So Lajero essentially is linear time in the size of the circuit. SumCheck is linear time in the size of the circuit. Lajero is sort of n log n in the size of the circuit and the witness. And this is why essentially the best of both worlds is to use SumCheck to produce a very small transcript about a circuit, and Lajero to basically give a zero-knowledge proof that the SumCheck verifier would have accepted a transcript. That is kind of essentially a one-step recursive composition, and that's the scheme that we've engineered. The SumCheck part is linear. The Lajero part is now essentially linear in the size of the SumCheck, n log n in the size of the SumCheck transcript, the SumCheck verifier. And so that's the second part that I'm highlighting here, and that is very efficient, okay? And it leads to a protocol of this form. And here I want to kind of give some rough performance numbers in the last few minutes. I want to leave time for questions. And so I think for the Polyhedra audience, the one major question, so Tian Chang and, in his PhD, he had a very nice line of work that shows that you can use linear time codes. And we have investigated using these, and instead we've selected Reed-Solomon. And that is because for the range of witness sizes that we need, okay, and that's essentially in this 2 to the 14 to 2 to the 16 size here, right? The commitment time using, so these are essentially on x84 and on Pixel phone devices, it's the time to do Reed-Solomon encoding for these type of sizes, okay? And you can sort of see for along all of the dimensions that we care about, essentially the time we're looking at, and we're using this top line, by the way, this is the best finite field with security that we need. We're taking about like between 1 and 4 milliseconds to do our Reed-Solomon encoding. Essentially, it's not anything to optimize. And when we work with linear time encodable codes, essentially the encoding time is already larger than our Reed-Solomon time for these particular parameters, okay? And moreover, the queries that are needed when you use a linear time encode are much, much larger. So here we use like about 180, so between 120 and 180 queries against our code when we use a Reed-Solomon scheme. And when we use a linear time code, we have to use about 6,000 queries. So it's essentially about 50 times more, 40 to 50 times more. And the time for our parameter regime is already more than essentially our code. So that's why we don't use linear time codes. And of course, the rest of our work, we focused very heavily on optimizing essentially the circuits that we use. And these are about, rough sizes for how big our circuits are. We have an ECDSA circuit, which is very small portion of the total amount of work. So just verifying one ECDSA is about 23,000 constraints or quads, whatever you want to call them. So it's very small. The time it takes to verify one ECDSA signature, it's about, the total time is about 60 milliseconds right here for one signature and 87 milliseconds for two signatures. And it goes to about 120 milliseconds on the phone, okay? If you look at other schemes, so for example, CIRCOM takes about 140 seconds versus 120 milliseconds, so it's about 1,000 times slower. And a recent work in S&P, they show an ECDSA circuit that also uses a SumCheck-based ZK system with different choices, about 900 milliseconds. So again, and that's on x86. So this is still about 15 times slower than our approach. And again, SHA-256 is the other major component. We have very robust and small arithmetizations for SHA-256, and our running time goes from like 10 milliseconds, depending for one block message to about 200 milliseconds for a, 32 block message. And if we compare that to Lajero, for example, it's about Lajero, just using Lajero by itself is about 25 times slower. And using Stark is, we ran the Stark prover with this type of problem and it was taking 106 seconds. So again, that's like more than 1,000 times more expensive than our system. And I guess that's kind of where I wanted to leave it. You can look at our paper for some more benchmarks, but hopefully what this talk did is explain to you what the problem was, which is giving a zero knowledge proof for legacy crypto. In particular, we really want to constrain ourselves to use exactly the schemes that drivers that like mobile driver licenses and passports are currently using. That makes it much easier to deploy because we don't need their cooperation to deploy zero knowledge. We can basically do it on top of whatever they issue. And now the issue becomes what proof system among the many that you can choose from should you use? We've taken one data point and we've optimized it and we've come to this particular conclusion. And as a result, I invite the community, especially the polyhedra community, to take a look at whether you can do something in your proof system that's comparable to this. We would love to discuss that. And I certainly encourage you, if you're a student in this thing, try taking any one small piece of this and trying to, as a hackathon, try to build a system in we've done the, small benchmarks like this. We haven't tried Polyhedra's very fast prover yet, but we'd love to hear we'd love to see some of the performance details. So is it available for use? Yes. So we've written our paper. We're currently trying to standardize this system in ISO as well as IETF, and we're also open sourcing our code. The thing is, I did this work. I'm an academic, but I did this work in Google, and so we're going through the Google open source process, which is very robust. And so we are doing a bunch of reviews on the code, and hopefully this spring will be, it's on a launch calendar to give you the sense of what that is. So it's on a launch calendar, which means hopefully this spring, all of the steps towards launching it as an open source project succeed, and that happens. In terms of being able to use it, that's the other motivation, is that if this works out and turns out all of the engineering issues get resolved and this becomes something that that can be deployed, you'll be able to use it with perhaps your Google Wallet and some relying party that wants to do age assurance. Next question: with your protocol, where are the bottlenecks with time input complexity? What proof parts do they impact the most? Good question. Let me go to one of the motivations for why we use this particular mechanism here. There are two components. We basically first produce a SumCheck transcript to verify the mobile driver's license. Those 5 steps that I showed you about how a mobile driver's license is verified, we have a circuit for that, and we use SumCheck to produce a transcript for that. That transcript is very small. It's a few hundred elements, essentially. And then we produce a Lajero proof that the SumCheck verifier would have verified that transcript. And now the running time, optimally, we would kind of balance these, okay? But as right now, essentially on small instances, Lajero is the bottleneck. On much, much larger instances, SumCheck becomes the bottleneck. Now, again, with SumCheck, you can do a number of things. You can change your circuit. You can change the number of layers of your circuit to kind of make it faster or slower. And that is, in fact, one thing that we are investigating now, how to automatically, quote, slice the circuit to make it to make it faster for SumCheck, produce a larger transcript, and thus require more time with Lajero, but essentially overall balance it to create to be faster overall. That in terms of asymptotics, again, the SumCheck part is linear, and the Lajero part is n log n in the size of the witness in the SumCheck transcript. However, those asymptotics don't. Asymptotically, you kind of want to minimize the size of your Lajero transcript, which is thus minimize the size of your witness and minimize the size of the SumCheck transcript. And but the thing is, that's usually very, very small. And as your instance size grows, then the SumCheck part, the linear part of the computation, begins to dominate. So I hope that answers your question. How do you get updates for it? Is there a dedicated channel? So again, so far, I told you that we have not, we're in the process of open sourcing our library. Once we open source it, it'll be available in what's called like the Open Wallet Foundation. They have a test wallet for these type of identity protocols, and hopefully you'll be able to play with it with that. But that's not going to happen until later in the spring. Can't we do this using ZK snarks? Like, what's the difference does this make from ZK snarks? Well, our scheme, what I've talked about today is a particular construction of a ZK snark. What I'm explaining to you is a ZK snark, and the other ZK snarks one can consider, right? So this is the family of ZK snarks that you can consider. By GRA16, I mean all of the ones that require trusted parameters and are extremely succinct, like the Plonkish and all of those other ones fit into that category. And we've basically decided that for this application, we don't want to explore things that require bilinear pairings or things that require trusted parameter setups, because for the legacy reasons that essentially it's very hard to deploy those type of cryptos onto new systems. It's very hard to deploy trusted parameter setups in this ecosystem. That leaves us with the rest of the world: Stark, Lajero, Hyrax, the Polyhedra SumCheck prover, which is new. It was released after we started this work. Stone, there's the S2 prover that Stark has as well. There are a few others. These are the schemes that we've been looking at, and we essentially, at a very high level, Stark-style provers have always had larger prover time, that we verified as well. They have smaller proofs but larger prover time. And in our application, because it's the user's phone that's making the proof, we're looking for proof systems that have smaller proof times and still reasonable proof sizes. So those are the set of constraints we've encountered in the engineering world, and these are, as a result, we've been driven to build a proof system like the one I've described. But in principle, you can use any ZK snark, and so if one has come up with a better one that works faster than ours for the problem that I've stated, we'd be very interested, and would be interested in collaborating. So we have just a few more minutes. I'm sorry I didn't get a chance to explain all of how this protocol works. I will share these slides. I will share the details of our circuits. You can, of course, all of this stuff is in our papers.
Abhi, if I can suggest, since there is no time limit, at least on our side, for hosting the event, if you have the flexibility to cover that section, you're perfectly welcome to do so. So I don't want to push you. Like, we do actually have the time. If you have the time, we're happy to go through this. I know there's a lot of questions. Everyone's really engaged, so we would love to see that part as well, if you have the time as well.
Sure. So let me just, I don't want to spend too much time, but I do want to basically, let me just make one more point then, essentially. So if we look at the statement that we're trying to prove here, let me leave it at that. So this is the statement that we're trying to prove. It involves two signature verifications, the P256. It involves two very big SHA computations, the SHA of the mobile driver's license and the SHA of the salted hash, and it requires one range proof. So ECDSA, SHA, and a range proof. Those are the tools that one needs in order to build a system for this application. What we figured out is that the part that's used to verify the signatures is very, very small. It's less than 10%. Most of our circuit is with verifying the hash. We've done a number of techniques where, for example, our proof system uses two finite fields and does something to verify consistency between those finite fields in order to optimize for this particular use case. And the ECDSA portion, I think, is well understood, and I'm not sure that anything will get faster with that. The approach that we've taken is very good with that. I do think there's a lot of room to improve our processing of SHA, okay? So this SHA circuit, it involves, as you see, SHA essentially involves ANDs, XORs, and rotations. Those all are very easy to arithmetize. And then addition mod 2 to the 32. This is the most expensive part of the SHA-2 circuit, especially it depends on which finite field you're using. And we've built a few techniques that allow us to verify addition faster than it takes to compute the addition bitwise. But I think there's probably more room in optimizing the SHA-256 verification. Now, many people say, why not use Poseidon or something else? Again, my answer to that is the legacy crypto that we inherit uses SHA-256, it uses ECDSA, and it uses a range check. And so really this is an exercise in changing crypto and finding the right crypto that optimizes these legacy optimizations. Sorry, these legacy choices. So I do think there's a research question about how to do SHA-256 most efficiently. These are our numbers for the circuit sizes. If you look at this quad term, that's essentially the best representation of our circuit size. Inputs also are important. So one of the main reasons our proof system works so well, this line right here, this F2 to the 128 packing of 2, essentially that represents the line we're using in our implementation. And that means that for each SHA block, we only need about 3,500 inputs, witness inputs. And that, of course, means that our commitment size can be very small. And of course, commitment is one of those things that takes super linear time. It takes the n log n time. And so this is one of our choices, but I think maybe there can be other choices. You can see the running time. We're able to basically prove SHA pre-image in about 11 milliseconds using our proof system. And I'm interested. I think there could be faster ways to do that, especially around the 32 block size. So yeah, let me just wrap up in 1 minute here, which is to say, I think there's a lot of possible work here. We've shown Lajero and Stark are not competitive, but I do think that other proof systems, Binius is an example, we've benchmarked part of that, And I think Polyhedra's proof system, I'd like to get some numbers from their proof system for SHA-256. If any of you in the audience are capable of doing that and working with me, please do reach out to me. And there's one question, what kind of hardware are these on? We tested on 2 hardware. One is an x86 64-bit platform. It's like a 4-core machine that you can get on GCP with 16 gigabytes of memory. And the second device, the more important device we test on, is the Pixel Pro hardware, Pixel Pro 6 phone. We run all our benchmarks on the phone because prover time on the phone is kind of the most important gating feature for this system. Anyway.
Fantastic. Thank you, Abhi, for this. I don't want to hold you for too long, but this was an amazing lecture, very thorough. As you can see, a lot of our participants enjoyed it. Thank you, everyone, for being today, for being here today. As again, the recording will be made available to you in the next 24 hours. And do tune in for tomorrow, as we're going to be having one more lecture, which is going to be from Siki Wang from Polyhedra, and it will be on utilizing the Expander compiler collector. Again, thank you so much for being here. Great workshop, and a nice way to round today's day of workshop with you, Abhi. Thank you so much.
Thank you for all your questions, and thank you for the invitation. Cheers, everybody.
See you around. See you tomorrow.